Hey, nice to see you again. So, yeah, I said that we're pretty close to being done with the prologue, so that, you know, supposedly now everyone should be at the same spot if you continue to watch all the videos so far, right? Well, okay, I have some, like, good news and bad news. I don't know. I mean, the good news is that, yeah, technically speaking, we're really close. I mean, I really just want to talk about exponents, and before that, I need to talk about functions, or at least I feel to. You'll see why. You'll see why when we get there. But uh, I do kind of do like an outline before every video, and the outline for this video, well, the outline for this video and the next one, they're pretty long. At least, so every video that I've done so far is supposed to be like a page, maybe 2 pages long, and somehow I always think, oh, it should only take 15 minutes. And no, right? They turn out to be 30, 45. I think it was 50 the last what the biggest one so far. So between the topic of today and the next video, between those two topics alone, I see that is equal to 5 pages. So it makes me think that is we're gonna have a gigantic video no matter what. I'm trying to put them. So depending on how this goes, either I'll put them together, or I will separate them to 2 videos. Maybe the second video has a part two. Depends how it goes, because at least kind of like the good news is that this time around, I'm just gonna be giving information, giving definitions and examples. So I think one of the biggest issues of why the axiom videos got so big is because, yeah, I wanted to prove everything so that you guys would get a hang of, get a taste of what mathematical proof is. This time around, I'm not gonna be proving anything. Like I said, I'm just gonna define some things and do some examples. So maybe if instead of me doing proofs, I just do examples and definitions. Hopefully, the video goes a lot smoother, a lot faster. The speed is what I'm looking at. Again, I always get sidetracked because I actually do like math, so I like to talk about it more and I like to expand on it. If someone just shows you one example, one example is nothing, right? You can't really, you need like a couple examples to kind of see some type of pattern, and that's why I like to like overdo examples. So yeah, so what's today's topic, right? Uh, I want to talk about functions. I've been saying that, right? Uh, if you've seen functions, but you probably haven't seen them this way. What's gonna be different is that I'm gonna give you guys like a big boy definition of what a function is, like a professional definition, and then you'll see the connections of what you come to know as a function and what I'm telling you is a function towards the end. Okay, more than that, once we talk about what a function is in general, I want to talk about a specific type of function, which is called the bijective functions. These are very special functions because it's going to turn out that bijective functions are the functions that have inverses. I mean, more or less, there's actually only one key idea about a function that needs to have in order for it to have an inverse. But again, I'm going to go really in depth, and that's what I'm saying, that it needs to be bijective. So yeah, the function part is going to be, I think, should be rather quick. It's everything we need to do up until bijective and inverse. That's where the bulk of it is. I mean, again, if it's just functions, I think from my notes it's just 2 pages, meaning that the other 3 pages are about more or less about, you know, how do you get to a bijective function? What does a function need to have to become bijective? So, like I said, who knows? Maybe the function part is only 15 minutes finally, Let's just say 20, right? Let's not be too optimistic. Um, and then if the bijective part turns out to be way bigger, that's what I'm saying. Maybe I'll do that as a part one, part two. All right. So before this video gets way too big, right? Just from the intro alone, let's get started. Okay, functions, right? Now, I did say that I'm going to give you like a professional definition of mathematics, right? I'm actually going to give you two. The one thing that I'm not going to give you is a perspective about relations. Um, it's something that you'll see, when we get to if we get to what you call it, real analysis. Relations are kind of interesting, but and again, some people use relations as a stepping point for functions. But again, I don't want to be too hard on you guys. The fact that I'm going to be really, I guess, strict or thorough. Not sure what the word is, right? Meaning, the things that I show you might seem hard, but I'm actually trying to make them as easy as possible. So yeah, like I said, I'm just letting you know there's a thing called relations, that two things are related, and it's kind of it's a good stepping stone for functions, but we're not gonna go there. Okay, so I did say before that a function has to, if a function goes from A to B, then it has something to do with A cross B, the Cartesian product, right? Okay, so definition, right? Let A and B be sets. A function f, let's say, right, from A to B is a subset of A cross B with the following properties. So what properties, right? Okay, so I'm saying that a function so far is just going to be some subset of A cross B, right? With some properties. Well, what are the properties? The first property is that for every A in A, there exists a B in B, such that the coordinate A comma B is in F. So yeah, right? It might seem awkward, but yeah, we're saying that F is a subset, right? So, we're looking at this as an element of a set. So for every element in A, there has to be some element in B such that this coordinate is an element of this set. The important part is really this part. Basically that every element, if we're saying that a function goes from here to here, that every element here goes to something in there. And the second property is the following. If suppose that A comma B is an element in F, and then suppose that A comma B prime is also an element in F, meaning as you can see, we have two coordinates where the first coordinate is the same thing, but I'm saying B prime as to say, these two might not be the same, right? Well, if we're gonna call this a function, if A comma B is in F and A comma B prime is in F, it must be the case that B equals B prime. So really what they're saying is that for every first coordinate, like let's say that A was equal to 1, if I'm saying that the coordinate 1 comma 5 is in F, and then something happens where, like, I'm deducing maybe that the coordinate 1 comma, let's say, X is in F. If I'm saying that 1 comma 5 is in F and I'm saying 1 comma X is in F, then I'm saying X can only be 5, meaning there can only be one the same second coordinate has to be associated with the first coordinate. Again, let's do an example, right? Because I'm pretty sure I butchered that up. Well, example. So suppose that E is the same set that we had on the last video. 1, 2, 3, 4. And then suppose that F is the same one that we had in the last video. 3, 4, 5, 6, 7, right? And again, you can look at the last video to know what E cross F is, right? Because I don't want to spend a long time in this video. So recall E cross F as a bunch of coordinates, right? Well, suppose that I say that F over here, and F is going to be, let's say 1, 5. That's one coordinate. 2, 4. 3, 6. And 4, 3. So this F, right, has these 4 coordinates, right? And as you can see, this is a subset of E cross F, right? Is it a function? Right? Is F a function? Is F a function? Well, let's see. Is it true that for every element in A, there's an element in B such that A, B is in F? Well, so again, it's saying that in this case, my capital E is my A, right? Well, I suppose I should say that since we're saying that F goes from A to B, we call A the domain and B is the codomain. Okay, so in this situation, E is the domain and F is the codomain. And what the first implication says is that everything in the domain has to go to something in the codomain. So for example, does 1 go anywhere? Well, apparently 1 goes to 5. Okay. Does 2 go anywhere? Well, I'm saying 2 goes to 4. And again, right, 5 is in F, so that's fine. 4 is in F, right? Does 3 go to somewhere in F? Well, I said that 3 goes to 6, really. And 6 is an element in F. And then I said 4 goes to 3. And yeah, 3 is an element in F, right? So far, it satisfies the first thing, right? The first condition is satisfied. What about the second condition, right? If A, B in F, and A, B prime in F, then B equals B prime. Well, what I'm saying is, so for example, the fact that I'm saying that 1, 5 is in F, the question is, do I have like a I don't know, like a 1, 3 in there, right? I don't. Do I have a 2, 4 here? Do I have a 2, 7 or something like that, right? Basically, do I have a 2, anything that's not 4? And I don't, right? Same thing for the 3, 6, right? I don't have a 3, anything other than 6. Same thing for 4, 3. So yeah, so this satisfies both of the properties. So then yeah, F is a function. And suppose now that, let's see here, say that G is 1, 5, 2, 4, 3, 6. Suppose that G now was this, you know, is this a function? Well, this G function. Well, it definitely passes 2, right? Again, you know, there's only 1, 5, 2, 4, and 3, 6. But it does not pass the first property, because again, it's very important. It says that for every element in A, there's an B in B such that A, B is in F, right? So 1 goes somewhere, 2 goes somewhere, 3 goes somewhere, but 4, where does 4 go? You know, there's no place for 4 to go anywhere. So yeah, this is not a function from. This is not a function from. I guess I should have said that better. G is not a function from A to B. But suppose that you had this other set D, and suppose that D was just 1, 2, 3. Then at this point, you could say that G is now a function from D to B, but not, again, G is not a function from A to B. Okay? Okay, and then again, another example, right? Just to make sure we get it, right? Suppose I have 1, 5, 2, 4, 2, 6, 3, 6, 4, 3. So what is it saying? That 1 goes to 5, 2 goes to 4, but I guess also 2 goes to 6, 3 goes to 6, and 4 goes to 3. So technically, again, is H a function from A to B? Right? Well, you can kind of say that the first property is satisfied. I mean, yeah, everything in A, or in this case E, went somewhere, right? But of course, right, this is not property 2 is not satisfied, because we're saying that 2, 4 is in F. I mean in H, and 2, 6 is also in H. But of course, 4 and 6 are not equal, right? Well, let me draw you a picture of each situation. Maybe this is gonna make maybe some more sense, right? Suppose that you have, let's see, right, over here, E. So E, F, and F. Right? So E is 1, 2, 3, 4, and F is 3, 4, 5, 6, 7. What does F do, right? It goes from here to here. Well, again, if you read back at it, right, F says that 1 goes to 5, 2 goes to 4, 3 goes to 6, and 4 goes to 3, right? And we said, yeah, this is a function from E to F. Nothing wrong, nothing out of the ordinary, right? Then we had, again, E and F. But this time it's G. Right? So we're going from here to here, right? 1, 2, 3, 4. 3, 4, 5, 6, 7. What happened this time? Well, we said 1 goes to 5. 2 goes to 4. 3 goes to 6. And then that was it, right? So the flaw here is that, in this type of representation, is that 4 didn't go anywhere. But the definition says that in order for you to be a function, 4 needs to go somewhere. So what's wrong in this picture is that the way that I'm drawing this is that if you're in the domain, there has to be some type of arrow connecting you. It doesn't matter where the arrow points at. It really doesn't. But there has to be some arrow that starts in E and lands somewhere in F, right? So yeah, the fact that 4 doesn't have some type of arrow doing that is kind of shows that it's not a function. That G is not a function. Okay, so one more time, E. That was H. We have F. 1, 2, 3, 4. 3, 4, 5, 6, 7. And what happened this time, right? Well, we said that 1 goes to 5. 2 goes to 4. But then we said 2 goes to 6. At least in H, right? 3 goes to 6. and 4 goes to 3. Right. So what was the problem here in this kind of picture representation? So believe it or not, the funny part is that you see how 2 and 4 go to 6, right? So you have 2 arrows pointing to 6. That actually is not a problem. That you know, that doesn't, that wasn't one of the conditions. You know, we're not, that actually doesn't break any condition at all, right? The condition is broken because it was 2 4 and 2 6. So basically, here's the error, right? This thing right here, the fact that one input is going to 2 different outputs, that's the part, that's the error, right? So yeah, in G the error was that one element in the domain didn't go anywhere, so that's bad. And then the second thing that's not allowed is that when an input goes to 2 outputs, right? That's the condition 2. So yeah, right. It's kind of weird that we're looking at functions and thinking of them as sets, right? Because the way that what I did here in these pictures is I'm saying, right, a function should send elements in one set to some elements in a different set. That's what a function does. It sends elements in one set to a different set. So that's why I'm going to give you a different definition, still valid, of what as a function should be. So starts the same. Let A and B be sets, right? A function f that goes from A to B is a mapping of every element in A which those are what we call inputs to some elements in B, which are the outputs. Okay, so how do we put this in like mathematical terms, right? That is, so the first is that for every A in A there exists a B in B such that f of A equals B. And then 2, well, I'm gonna put it this way. If A let me do this. Well, actually, suppose that A1 and A2 are both elements in the domain, right? If A1 equals A2, then f of A1 needs to be equal to f of A2. And this is what we call a function being well defined. So what am I really saying here? I'm saying, you know, suppose that you have 2 quantities that maybe they don't look the same, but they're equal, right? Because again, that's basically all of algebra. That happens a lot. If 2 elements are equal, even though they might look different, if f really is a function, then it needs to map the same element, you know, to the same place. Again, we don't wanna have this situation where 2 goes to 4 one day and in a different day 2 goes to 6, right? So if 2 elements are the same, even if they look different, then the outputs have to be the same. So if A1 equals A2, then f of A1 has to equal f of A2. Again, that's what we call well defined. So yeah, I mean, you know, I'm pretty sure, you know, this definition is equivalent to this one. I mean, because that's really what it means, right? If again, the fun thing is that we're looking at functions here in this definition as sets, and there is there is a merit to that. Like, you know, if you think, oh well, that's silly, well, you know, you're gonna see the merits in the future. But yeah, it implies also that if we're calling f, for example, a function, it implies that what I've been saying, that 1 goes to 5, 2 goes to 4, 3 goes to 6, and 4 goes to 3. You know? So when I say, I forget to say, right? So when I say if a b equals f and a comma b prime equals f, then b equals b prime, I mean, that's kind of what I'm saying, you know? I don't know. If you don't think so, if you don't think they're really equivalent, you know, drop it down in the comments, right? So what, again, this is what I'm saying. Example. If you say, let, I don't know, f from the real numbers to the real numbers be f of x equals to, I don't know, x squared, right? This is equivalent to saying that your function f is all xy in real numbers cross real numbers, which is just r squared. If I say r squared, I really just means r cross r, right? So yeah, when I say a function from real numbers to real numbers, so that f of x equals x squared, this is equal for me to say that f of f as a set is, right, all the coordinates in the, you know, two-dimensional plane such that the second coordinate equals x squared. Okay, so this is how you go from back and forth, because again, in high school, or just, you know, in your college algebra or whatever, you only see functions this way, right? They probably don't even mention the fact that you know, your functions go to real numbers, because yeah, everything you do is in the two-dimensional plane, right? But just so you know, this whole thing, it's the same thing as just saying, yeah, that it's a set, because it's the picture of the graph, right? It's all the coordinates that satisfy y equals x squared, right? Alright, well, let's see. I see, you know, I'm looking at the timer, and it's messing me up. Well, let's see. I mean, there's only one thing to see. Is this really a function? Does it actually pass both the conditions, right? Well, I don't know. Let's do. If I do this real quick, right? Real numbers to real numbers, right? And this is my f. That's going this way, right? Well, okay. 0, -1, -2. Let's say, I don't know, -3. 1, 2, 3, right? And then the real numbers, the same thing, right? 0, -1, -2, -3, 1, 2, 3. I know it's really small, but you know. Well, okay. So if f of x equals x squared, right? Where does 0 go? 0 goes to 0 squared. 0 squared is 0. Okay. 1 squared equals 1. So 1 goes to 1. 2 squared equals 4. Well, so I didn't put in this list here, right? But you definitely know it's a real number, right? 3 squared goes to 9, which again is not here, but you definitely know it goes to a real number. What about -1? -1 squared is a positive 1, so then it goes here. -2 is a positive 4, so it goes with the positive 4. And -3 squared is a positive 9, so it goes with the positive 9. So does it look like a function so far, right? Well, I think so, right? So far, it's looking like every element in the domain is going somewhere, right? And on top of that, it doesn't look like any input is going to two different outputs. Now you might be thinking, well, look at what's happening. Not only the 2 get ignored, well, not really, but all the negatives are getting ignored. So are you okay with that? The answer to that is yes. You know, we never said that every output, or we never said that everything in the codomain has to be hit. So yeah, the fact that it satisfies the first property and the second property looks like it is a function. Well, again, right? So you're more used to this instead. Suppose that this is the x-axis and the y-axis, right? So you probably know that the way this thing looks is like it's a parabola. It looks like a U, right? I mean, how would you know that even if you didn't know? Well, you can always plug in points, x, y. So for example, that's kind of what we did here. 0 goes to 0, 1 goes to 1, 2 goes to 4, but -2 goes to also +4. -3 goes to +9. +3 goes to 9, right? So again, let's say that 1 is right here, and it goes to 1. 2 is right here, so it goes to 4. So again, what I'm trying to say actually, let's say that it goes to 9. So here's what I mean, that everything in the domain is being touched, right? -1, -2, -3. The domain is the x-axis, and my question is there a y value according to this picture? Is there a y value for every x value? Well, again, right, if it's 1, it goes to 1. If it's 2, it goes to 4. If it goes to 3, it goes to 9. But what about, again, the 2, let's say that 2 is right here. Did 2 really get ignored? No, because there's a number called square root of 2 that's right here, and it goes to 2, right? Basically, any number you can think of goes to some other number in this fashion, right? They go like that, right? And again, if you see some flaw in the picture, it's just my fault, right? But what I'm saying is that, yeah, so far every positive number is going to some y value, right? Well, the negatives too, right? -1, according to this picture, goes to 1. So you see what I'm saying? I'm tracing, basically. I'm picking it up from the domain, going up to the picture, and then tracing the y value that should go along with it, right? Right? Well, the picture will be infinite. So, okay, so yeah, what I'm saying is that, yeah, how do you check that everything in the domain is going somewhere? Well, it is, I mean, think of a number, square it, that's where it goes to. So let's just say that it satisfies the first property. What about the second property? Does every x value only go to one y value? So far that it's looking that way, right? Every x value is going to one y value, right? So basically, what this means is something we call the vertical line test. The only way that something only has one y value for each x value is if it passes the vertical line test. Meaning, imagine this is my line. Does this line only touch the graph, which is a parabola, once at all times? It's only touching once, it's only touching once, it's only touching once. Yeah, right? I mean, you can say that, yes, right? This vertical line only touches the graph at one time for every x value, right? So that's basically the test of what you do to see that your function is well defined. Well, the fact that I already went that far means to show you what isn't a function, right? So now I gotta show you what is not a function. And the most famous thing I can show you that's not a function, the thing that pretty much everyone sees, is basically this, right? Let G be all the coordinates x, y in R square. Again, that just means R cross R, such that x squared plus y squared equals 1. Yeah, so all the coordinates are such that x squared plus y squared equals 1. Well, I don't know if you knew this, but this turns out to be a circle. In particular, a circle of radius 1. So, I don't know, maybe let me take it from here. So say that this is a 1. This is -1. So what will be like? Maybe ones right here, and then maybe negative ones right here, right? So yeah, believe it or not, if you look at this as a set, the set of all points that satisfies this equation, it turns out for for some weird reason, right, that it's a circle. It's actually not a weird reason, but we need some knowledge in geometry to explain it, right? Okay, so again, right, the first definition says it's completely okay to look at functions as sets. So is this set a function? Well, it kind of depends. If you said g is a function from R to R, because we're looking at this coordinates in R cross R, the answer to that is no. Why? Because again, the first condition says it fails the first condition, because let's say for example, of course 2 is a real number, right? 2 is in the domain, but 2 comma anything is not in this function. What is here? In this function you have the point. This is x and this is y, right? You have the point 1 comma 0 is this one. This is the point 0 comma negative 1. This is a point 0 comma positive 1. This is a point negative 1 comma 0, right? I think if 1/2 is right here, right, this point right here will be the point 1/2 comma square root 3 over 2, because if you notice, if you plug in x equals 1/2 and y equals square root 3 over 2 into this equation, you will get 1, right? So yeah, right. So what does this mean? So you could see, for example, that like for example 1/2 goes to maybe square root 3 over 2, right? This number goes to whatever the y value is here, This number goes to whatever y value is here. But 2 is over here, right? 2 is going to be over here if we extend this real number line. If I look up or down, there's no picture. And that's what it means that 2 doesn't go anywhere. Yeah, so because 2 comma R, because 2 is in R, but 2 comma anything is not in my G, right? Meaning there's no y value such that 2 comma y is in G. Okay, so then maybe, but that's not a problem. Okay, so far, maybe let's say that G is a function that goes from -1 to +1, and then it goes to the real numbers, So now we're saying, okay, yeah, right. If a number is between -1 and 1, then yeah, I can kind of trace it actually. But actually, but then, even if you do that, it fails. Still no. It still fails the second property. Well, what I mean, I kind of show you already right here, right? 0 comma 1 is in G, but also 0 comma -1 is in G. And we said that if it's and clearly 1 is not equal to -1, right? So this is not supposed to happen if G is a function. And it's not just 0, 1 and 0, -1, like I said, I just said that 1/2 comma square root 3 over 2 is in here, but if you trace it down, well, it only makes sense that 1/2, comma square root 3 over 2 negative square root 3 over 2 is also there, Basically, it breaks the vertical line all the time. I mean, the only time it doesn't break it is right here at the endpoint, right? And then it breaks it all the time. You see this vertical line is crossing the function at 2 points, even though it's only supposed to cross at 1. And then you get to this other endpoint, and again, okay, only at this endpoint and at this endpoint does the vertical line only touch the function once. Again, if it happens once, it's bad. It happens basically almost all the time, right? So no, so actually, yeah, even if you try to make it fit, G is not a function. What the best we can do actually is this, you know. So suppose you have x squared plus y squared equals 1, and then say that you solve for y. Say that you're solving for y, right? So then you're gonna subtract x squared. You're gonna have y squared equals 1 minus x squared. And then we don't know that we can do this yet, or do you? Have you been proving real number facts? We don't know that we can do this, right? But suppose that you square root, then square root, and you're gonna get that y equals plus or minus square root 1 minus x squared, right? So what I'm trying to tell you is this. Yeah, this is not a function. It fails a lot of things, right? But if you say, let, you know, for example, f be x and y in R2 such that y equals positive square root of 1 minus x squared, and if you let g equal all the coordinates in R2 such that y equals negative square root of 1 minus x squared, right? If you do this, right, then f, this f right here, would actually be the top part of the circle. And if you let this be g, g will be the bottom part of the circle. So then at this point you could say that, oh, I forgot. This wasn't supposed to be g. It's supposed to be h. Because this is g. Right? So if you do that, you can say that g is a union of functions. G is basically the union of f and h. This was supposed to be h, right? So maybe even things that even sets, you know, this is why set the set perspective is kind of fun, because yeah, g might not be a, you know, it's a set, but it's not a function, right? But it could be a union of functions, right? So two things about this is that it shows that the union of two functions is not a function. It's not a new function, right? What conditions can you make? What conditions can you add so that the union of two functions is a function? Is a function. And the only thing I want to say about that is, you know, well, kind of like as a hint, maybe, I don't know, right? If we could only suppose that you have your circle, your unit circle, right? The top part is a function, and the bottom part is a function, right? If only we could shift the red part, right, to maybe now, so that it now looks like this. So that the, right? Suppose we shift the red to the right so that now the red part sits like right here, right? It's not to scale. Don't make fun of me. But in this situation, right, now we would have that the union of two functions does give you a function, right? Because this will pass the vertical line test, right? So yeah, I don't know. I'm just gonna leave you with that. What condition do you think you can add so that now the union of two functions is a function, right? Alright, well, of course it turned out to be a big video, right? But if you feel like you learned something, maybe leave a like, leave a comment. I think you're gonna learn more in the next video for sure. But yeah, now you can, so if anything, now you know what is and isn't a function. You know, now you know there's a test for testing if it's function, and then now you know that, you know, functions aren't really just, you know, in your college classes you're always going to see, yeah, functions from real numbers to real numbers, and that's what you work with, r squared, right? But hey, you can make a function from anywhere to anywhere, and now you know how. Now you know the conditions that it needs to be so that you can call something a function. But alright, I'll leave you guys there. Thank you for watching.